Alright, so we've taken a quick look at rotational motion, and if you did the previous problem, you'll hopefully have seen qualitatively that when we change the radius of a wheel, the distance that the points on the wheel travel change. For example, if you have a tricycle with a wheel with a circumference of 1 meter, if you turn the pedal around 360 degrees or 2 pi radians, then the trike will move forward 1 meter. Notice the circumference is 1 meter, the radius would be about 16 centimeters. So if you doubled the radius to 32 centimeters and the circumference to 2 meters, then the bike would travel 2 meters for every rotation of the pedal. Alright, so we want to clarify our analogy here between rotational motion and linear motion. In linear motion, acceleration, a, is the change in velocity divided by the change in time. Acceleration is a vector, as is velocity, and if you know the change in velocity, then you can divide it by the time to find the acceleration. For angular acceleration, it too is a vector, and it is the change in the angular velocity divided by the change in time. Notice again, angular velocity is also a vector. For velocity, the velocity is the change in position divided by time. It's a vector as well, and if something is under constant acceleration, then the final velocity is equal to the initial velocity, v naught, plus the acceleration times time. For angular velocity, it's the change in the angle divided by time, and under constant angular acceleration, the final angular velocity is the initial angular velocity plus the angular acceleration times time. Notice these formulas are exactly the same. For position under constant acceleration, you can take the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared to get the final position. It may seem like a very long time ago, but you've done a bunch of problems like this before. For angular position, it's pretty much the same thing, right? You do the final angular position is the initial angular position plus the angular velocity times time plus 1/2 the angular acceleration times time squared. So this is great. If you understand the interplay between position, velocity, and acceleration, then you can pick up the understanding of the relationship between the angle, the angular velocity, and the angular acceleration pretty easily. If we want to check the relationship between the two, we can multiply the angle by the radius to get the arc distance, the angular velocity by the radius to get the velocity, and the angular acceleration by the radius to get the linear acceleration. So imagine if we have a tricycle situation we talked about earlier. If you know how far the wheel has turned in radians, you can just multiply it by the radius of the wheel to get how far the trike has traveled. The relationship also holds up for velocity and acceleration as well. Angular motion works in pretty much the same way as linear motion, except we're looking at angular position, angular velocity, and angular acceleration. So we can use the exact same strategies that we use to understand linear motion and use those to understand rotational motion. So let's try our problem here. We have a cyclist that starts from rest and pedals such that the wheels of the bike have a constant angular acceleration. After 30 seconds, the wheels have made 80 revolutions. Our first question is, if the radius of the wheel is 40 centimeters, how far did the bike travel? Well, we know that the wheels of the bike have made 80 revolutions, so the angular distance that the wheels have traveled is 2 pi radians per rotation, so that is 160 pi radians. 160 pi radians is 502.6 radians, so we can use that to get the distance. The distance is the radians turned multiplied by the radius, so that is 503 radians times the 0.4 meters for the radius, and that gives us a distance of about 201 meters. Our follow-up question is what is the angular velocity at 30 seconds? This is pretty much a question that you guys have answered half a dozen times before. If you were given a distance traveled from rest and a time, then you can find the average velocity by taking the distance traveled dividing by time. Then, since the average velocity is the initial velocity plus final velocity divided by 2, the final velocity is twice the average because the initial velocity was 0 because we started from rest. Well, this question is exactly the same, except we're doing it with rotation rather than linear distance. So we previously found out that the wheel rotated 503 radians in the 30 seconds. So that means we want to divide the 503 radians by 30 seconds to get the average angular velocity. That gives us 16.77 radians per second for the average angular velocity. Notice this is the average omega, or angular velocity, not the final that we've been asked for. So the average angular velocity is the initial angular velocity plus the final angular velocity divided by 2. So that means the initial angular velocity is 0, since the bike starts at rest. Then the final angular velocity is twice that. It's 33.5 radians per second. Notice that if you wanted the angular acceleration, you could proceed exactly as you did before. You have the change in angular velocity, and so then you would take that and divide by 30 seconds, the time. So if you did that, that would give you about 1.12 radians per second squared for your angular acceleration. So basically the same strategy that you did before in this race car accelerates from 0 question. Okay, I think you have a pretty similar question for you guys to do, so good luck.